The periodic table of elements is a cornerstone of chemistry, providing a systematic arrangement of elements based on their atomic structure and chemical properties. It's a powerful tool that allows scientists to predict the behavior of elements and understand their relationships. However, there's one element that stubbornly resists neat categorization: hydrogen. Despite being the simplest and most abundant element in the universe, hydrogen's placement in the periodic table remains a subject of debate among chemists. The periodic table, a work in progress. Before delving into hydrogen's peculiar status, it's crucial to understand that the periodic table, despite its apparent immutability, is a dynamic scientific tool that continues to evolve. Its fundamental principle is the arrangement of elements in order of ascending atomic number, which corresponds to the number of protons in an atom's nucleus. This arrangement reveals periodic trends in elemental properties due to the electron configuration of atoms. As electrons fill specific subshells around the nucleus, patterns emerge in chemical behavior. When a subshell is filled, the pattern essentially repeats in the next row of the table. This periodicity allows elements to be grouped into columns, groups, with similar chemical properties. The hydrogen conundrum. Hydrogen, with its single proton and electron, seems deceptively simple. Yet, this simplicity is precisely what makes it so difficult to place within the periodic table's structured framework. There are at least 3 credible positions where hydrogen could be placed, each with its own justification and drawbacks. Group 1 alkali metals, Group 14 carbon group, Group 17 halogens. Let's examine each of these potential placements and the reasoning behind them. Hydrogen as an alkali metal, Group 1. The most common placement of hydrogen is at the top of Group 1, above lithium. This position is often chosen more by convention than by strict chemical logic. The arguments for this placement include single valence electron. Like alkali metals, hydrogen has 1 electron in its outermost shell. Similar ion formation. Hydrogen can form a positive ion, H+, by losing its electron, similar to how alkali metals form Na+, K+, etc. Reactivity with halogens. Hydrogen reacts with halogens to form compounds, e.g. HCl, as do alkali metals, e.g. NaCl. However, there are significant differences that make this placement problematic. Physical state. Hydrogen is a gas at room temperature, while alkali metals are solid. Metallic properties. Under normal conditions, hydrogen does not exhibit metallic properties like electrical conductivity or metallic luster. Compound differences. While hydrogen forms compounds with halogens, these compounds often have very different properties from their alkali metal counterparts. HCl is a gas. NaCl is a solid salt. Hydrogen in the carbon group, Group 14. Some chemists argue for placing hydrogen at the top of Group 14, above carbon. The rationale includes similar electronegativity. Hydrogen and carbon have very similar electronegativities, meaning they share electrons relatively equally in bonds. Covalent bonding. Like carbon, hydrogen primarily forms covalent bonds rather than ionic bonds. Tetravalent behavior. In some compounds, a single hydrogen can be replaced by a CH3 group without significantly altering the compound's properties, suggesting some similarity in behavior. The main argument against this placement is the significant difference in the number of valence electrons, 1 for hydrogen, 4 for carbon, which leads to very different bonding patterns and molecular geometries. Hydrogen as a halogen, Group 17. The case for placing hydrogen at the top of Group 17 above fluorine rests on these points. Electron acceptance. Like halogens, hydrogen can gain an electron to form a negative ion H, analogous to F-, Cl-, etc. Diatomic molecules. Hydrogen exists as a diatomic molecule, H2, at room temperature, as do halogens F2, Cl2, etc. Similar compounds. Hydrogen forms similar compounds to halogens in some cases, such as hydrides, e.g., Na, which are analogous to halides, e.g. NaCl. The main counterargument is that hydrogen is much less electronegative than fluorine and other halogens, and doesn't share their extreme electron-grabbing tendencies. The implications of hydrogen's placement. The debate over hydrogen's position in the periodic table is more than an academic exercise. The periodic table is a predictive tool, and an element's placement should allow for accurate predictions of its properties and behavior. Misplacing an element can lead to incorrect assumptions and predictions. For instance, if hydrogen is grouped with alkali metals, one might incorrectly predict that it forms ionic compounds with halogens, when in fact it forms covalent compounds. Placing it with carbon might lead to false expectations about its ability to form complex molecules. Grouping it with halogens could result in overestimating its electronegativity and reactivity. These potential misunderstandings highlight the importance of finding the most appropriate placement for hydrogen. Alternative solutions. Given the difficulties in placing hydrogen in any single group, some alternative approaches have been proposed. Dual placement. Some periodic tables show hydrogen in both Group 1 and Group 17, acknowledging its ability to behave like both. Separate section. Some tables place hydrogen in its own section, separate from the main groups, to emphasize its unique status. Central placement. A few designs position hydrogen in the center of the periodic table, symbolizing its connection to multiple groups. Each of these solutions has its merits, but none has achieved universal acceptance. The uniqueness of hydrogen. The difficulty in classifying hydrogen stems from its unique properties. Simplest atom. With only one proton and one electron, hydrogen is structurally different from all other elements. Lack of core electrons. Unlike other elements, hydrogen has no inner electron shells, which significantly affects its chemical behavior. Quantum effects. Due to its small size, quantum effects play a more significant role in hydrogen's behavior compared to larger atoms. Diverse bonding. Hydrogen can form ionic, covalent, and even metallic bonds under extreme conditions, displaying a versatility unmatched by other elements. These factors combine to make hydrogen a truly exceptional element that defies easy classification within the periodic table's framework. Conclusion. Embracing hydrogen's complexity. The ongoing debate about hydrogen's placement in the periodic table serves as a reminder that even the most fundamental aspects of chemistry can be complex and nuanced. Rather than viewing this as a problem to be solved, we can appreciate it as an opportunity to deepen our understanding of atomic structure and chemical behavior. Hydrogen's resistance to simple classification highlights the limitations of any organizational system in fully capturing the complexity of nature. It challenges us to think beyond rigid categories and appreciate the continuum of chemical properties that exists among elements. For students and teachers of chemistry, the hydrogen debate offers valuable lessons: the importance of critical thinking in science, the evolving nature of scientific knowledge and tools, the limitations of models in representing natural phenomena, the value of understanding exceptions and edge cases in scientific classification. As we continue to refine our understanding of chemistry and atomic structure, the question of hydrogen's placement may eventually find a definitive answer. Until then, its ambiguous status serves as a humbling reminder of the complexity of the atomic world and the ongoing nature of scientific inquiry. In the end, perhaps we should embrace hydrogen's unique status. Its ability to defy simple categorization is not a flaw, but a feature that makes it one of the most fascinating and important elements in the universe. After all, in science as in life, it's often the exceptions that prove most illuminating.